Hello, students. So we're going to prove this thing right here. And I should add that these are all eigenvalues with eigenvectors for some transformation t. But it really doesn't matter what we call the transformation, but they're all for the same transformation t. So this is for some t that goes v to v. You can stick that near the top over there. So we have some transformation. It's fixed. It has eigenvalues. And I'm picking some collection of distinct eigenvalues, and these are their eigenvectors. So each of these is different. And what I'm going to do now is I'm going to show you that those vectors must be linearly independent. Okay, so proof. Well, let's suppose not. So suppose v1 through vm is dependent. Now remember that if we have a dependent set of vectors, that means not only is one a multiple of the others, but one must be a multiple of ones that come before it. So we're going to let n be the smallest number. So that v1 through vn, or I'll say this so that this is a better way to think about it. Vn is in the span of those before it. There we go. So if it's dependent, there must be at least one situation where some vector is in the span of those that come before it. And if there's one, we could always pick the smallest one, right? Because these are integers, and the integers are well ordered. We could always pick the smallest integer in a set, a non-empty set of integers. Okay. So what do we know now? Well, we know that Vn is a linear combination of these. So we can write Vn equals alpha 1 V1 plus alpha 2 V2 plus alpha Vn minus 1. So we're writing this vector Vn like this. Okay. Now, what happens if I apply t to both sides? So I put this in t and I put this in t. These are the same thing. So if they're the same thing, then when I put them into t, I have to get out the same thing, because they were the same thing before I put them in t. Okay, so I know t of Vn equals t of this. I'll just do that frustrating thing to you guys there. So t, where this is just placed there. And what do I know? Well, t is linear. So and we still haven't used the fact that these are eigenvectors. And we have to use that. So what do I know? Well, this gives me lambda n Vn, and this gives me alpha 1 lambda 1 V1, right? Because that's the eigenvalue for V1. And I get alpha 2 lambda 2 V2 plus dot dot dot. And this would give me lambda n minus 1 Vn minus 1. Okay, so now we've used the fact that these are actually eigenvectors. So I get this. So now where do I go from here? Well, I know that lambda n Vn equals this. And I got this from taking t of both sides. But I also have this. And, I always tell you guys, if you don't know what you're doing, you could always think about plugging. And you might say, okay, well, this is a Vn and this is a lambda n Vn. And yeah, I could plug this in as is, or I could just multiply lambda n to both sides. So I could say also, by multiplying lambda n to both sides, lambda n Vn is equal to alpha 1 lambda n v1 plus alpha 2 lambda n v2 plus dot 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 alpha n minus 1 lambda n vn minus 1. So I'm getting this by multiplying this by lambda n. And why would I think to do that? Well, because then these two are equal. Okay? So I could set this equal to this, or I could subtract everything over to one end, subtract everything to one side, or I could just subtract his equations and get this minus this equals this minus this. So I know that 0 happens to equal to what? Alpha 1 lambda 1 minus lambda n v1 plus alpha 2 lambda 2 minus lambda n v2 plus dot 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 plus alpha n minus 1 lambda n minus lambda lambda n minus 1 minus lambda n. There we go. Vn minus 1. What have I concluded? Well, Vn minus 1 is in the span of the terms before it, because I could always write this as lambda n minus 1 lambda n. I'll take the negative by switching the position of these two. And this goes all the way up to alpha n minus 2 lambda n minus 2 minus lambda n v n minus 2. Sorry for squeezing that in there. But basically, the only thing I did is I took this and I moved it over to the other side. And instead of putting a minus sign, I just switched the order which these two appeared. So we know that v sub n minus 1 is in the span of the vectors before it. But what was our main assumption? Our main assumption was that we picked the smallest number so that Vn was in the span of those before it, and that was n. So this can't be the smallest one that's a linear combination of vectors before it. If Vn minus 1 is a linear combination of vectors that come before it, which is a contradiction. This contradicts that Vn was the first vector in the list. So, which was a linear combination of vectors before it. And that is our proof. So, much like many of the different proofs that the square root of 2 is irrational or something like that, you make an assumption that something is in the lowest terms in the beginning, and then you contradict it by saying, but there was a lower way to express it. Like there was a that wasn't in the lowest terms because we could divide the top and the bottom. And that's sort of what we're doing here. We're saying, okay, we're going to assume that this is the first vector, which is a linear combination of those before it, and we show that there must have been one before it. Which both of these proofs, you could also think about the contradictions as saying that there must be an infinite chain, right? Because whatever number we try, whatever number we pick here, that ends up representing v sub n as a collection of vectors before it. There'll always be a lower one. And similarly with the proof that the square root of 2 is irrational, you could say, well, whatever terms you pick, there'll always be a lower one. So, they both come down to the well-ordering property of the natural numbers, the positive integers, which are well-ordered. And that's it. That's the proof. So difficult result, not a short proof, but hopefully each of the steps themselves were clear, and it was clear where to go at each point.